or any selection of terms equivalent.
Yeah.
Yes.
But if you use the cover rate instead of the true positive rate and the PQ instead of the false positive rate,
The coverage is the same as the positive rate.
yeah, okay.
Or, yes.
But if you use the PQ instead of FPR,
Yes.
then what you do is the false positive that you predict, so it's the rate of false positives you predict, basically. Not, yeah.
Alright, so we wrote it down here again, right? So
basically, which hits are false, that should not, or that should be, or
right.
which hits you think are true should be false.
So what you're comparing, right, is the true positive rate, which is this cell divided by this column,
Yeah.
versus the error per query, which is again this cell divided by this row.
Yeah.
Which of these cells are we now not using at all?
True negative.
This one, right? We started this lecture by reminding ourselves, oh wait, this does not mirror to the, doesn't matter, we'll figure that out in a sec. We started by saying that the total number of possible combinations is the amount of sequences squared divided by 2. How many of those do we expect to be actual homologs? So interesting to our benchmark. By order of magnitude, is this a tiny fraction? Is this almost half the data set?
I think maybe a tenth at most if you do better.
A tenth at most. Okay. So that means that the lion's share of all our weight will be in this cell. Or at least in this row. Correct? But the vast majority of relations that we're looking at are in reality not homologs. So then if this column has a lot of weight in our benchmark, what you're now comparing is not necessarily how many you get right, but rather how many homologs there were to begin with. Non-homologs there were to begin with. Does this seem like something that you'd want to visually compare your benchmark methods? Because I'm not sure if you've looked at the numbers in your query plots. We have a slide on this later on, but I can't pull that up on the beamer right now. Try something real quick. Does this work? It's doing something? Yes. Yes. So this plot, right? No, this is about the SAS rules. Next one then. Is it this one? Yes. This already gives away part of the question, answer to the next question, so don't read too closely. The average amount of well, the numbers of errors per query here for BLAST are about 1-to-1 at this point. But for the other methods, the coverage is much higher than the error per query. And this is what we want to see, right? If you were to make a rock plot of these things, they would be far closer, so the curves wouldn't separate as nicely. So this is a far more intuitive way to inspect how these methods compare between each other. Let's go to question 2 now. We were just on this. How do the different methods compare? And can we divide them sensibly into groups that perform differently based on something? So what would you separate the groups on, and how does their performance compare? Yes.
Okay, so if you can refer to the consideration that we're doing sequence analysis, sequence profiling, profile.
All right. So to make sure that everyone heard, he would classify the methods based on sequence or pairwise methods, sequence profile methods, or profile methods, which is the same distinction that they make in the paper. Correct?
Yeah.
Yes.
Something like But what I really like, what I think is important to remember is like the benchmarking methods, like the Alphos and Topit, because that's where it kind of makes it more innovative. Because that's when the combinations of the methods actually go into play. That's where that's more important, because if not, it's not really relevant if they just compare them. So whenever they do like combining profile sequence methods, they determined that's where they kind of determined like they were able to get a much larger performance. And like one of these like methods like comparison was using SAM and Cybus.
Right. So to slightly reiterate and rephrase, you can divide the methods themselves into different performing groups based on the input. So sequence, sequence profile, profile. Right? And if you make the plots for those individual methods, this is what you were not supposed to peek at earlier. Here, you see that these separate rather cleanly, right? So the sequence methods alone perform worse than the sequence profile methods, and the profile methods perform best by far. Now, not strictly part of the question, but also a relevant answer, is that if you go beyond this and consider the different types of data set that they try to compare against, or that they use for their ground truth. Where were we? Right. There the combinations of methods come into play. So the paper is about whether or not you can combine methods to improve your coverage of midnight zone sequences or homologs that have less than 10% sequence identity. And there again, the combination of these methods work best, and profile methods tend to do better than sequence methods. So I guess the take home for this one is that the type of information that your method uses, single sequence, or profile information, or a mix of the two, is determinant for how well it can perform to begin with. All right, question 3. Which database was used here to benchmark against? Would you use the same database, plus or minus y? Any takers? Has someone come across the term CAP? Who wants to tell me a little about CAP? Go for it.
So the CAP database, they have used two different versions of it. The number 35 and number 10 they call it. The number 35 has a 35% sequence identity and an 80% overlap of the cutoff. Bidirected multi-links clustering, which means that it is somewhat specific, pretty specific actually, because it needs 35% sequence identity to even cluster them to a certain family. And the number 10 is a lot less specific. It only has a 10% sequence identity and a 60% overlap cutoff. And if you use both of those methods together, it means you're going to have a lot of false negatives. No? False? Yeah. True negatives? Sorry, confused. One of either. Because you have also included some very highly non-specific sequences that were linked to a certain superfamily.
Okay. So, I've heard a lot of people refer to them as number 10 and number 35. The NR actually stands for non-redundant. And then the number that follows is an indication of what that redundancy threshold is. In this case, as has been mentioned, non-redundant 10 means that there is a 10% sequence identity threshold, and for NR35, that threshold is 35%. Would you use the same database for your project?
No.
Instead of, say, Go or PFAM or SCORE or whichever your group has been assigned. Why would you or why would you not?
I wouldn't, because you get way too much data that is completely not relevant.
Not relevant in what sense?
As in, if you only have a 10% sequence identity, you have a very big chance that it will find what it thinks are homologs, but which are completely not actually close to being homologs.
Okay. So his answer is, I would not use the NR10 or NR35 cath-derived databases because you think that high sequence identity occurred by chance rather than shared ancestry. Is that a correct interpretation? Yes? Okay. What about the structure information there, though? Is that still not indicative of shared ancestry?
The structuring is more indicative.
All right, and what does cath give you? All right, so cath is, like SCOP, a classification of proteins based on structural similarities. And in the, I think, next couple of slides, we will come to a slight correction that you can make on that. But the de facto standard for benchmarking sequence-based homology detection methods is structure-based methods. And then the authors make a big point about how we want to enrich this structure information with, say, functional annotations, or things we mentioned together in literature, or additional lines of evidence to support that two proteins share evolutionary ancestry beyond them sharing a structure. And that point specifically is also very important for the fourth question. So, who dares? Okay. Question about 3 first then.
Yeah, what occurred to me why they choose for cath rather than for SCOP. They introduced them as being quite similar, I think. But then they continued with cath, and it was unclear to me why that choice was made.
All right. I haven't read the author's minds, so I'm not 100% certain either, but I dare hazard a guess, which is that SCOP is, for the most part, and especially was at the time of his writing, manually curated entirely. So there is less entries in SCOP simply because it takes more work to put them in. cath is also for a very large part manually curated, but it is computer assisted. So they have some clever algorithms that predict whether or not two structures are homologous, and then a human expert only has to confirm it. Whereas the genius behind SCOP is Alexei Merzin, and he just looks at the structures and classifies them as whatever classification he comes up with. Very impressive man, very scary to talk to, but he is really good with protein structures. So if I had to guess,
Can I
cath is
add
much bigger.
one small thing? There's an additional simpler explanation, is that the Janet Thornton is the lead author on this paper as well as the lead author of cath.
See, this I did not know, but it is indeed a much simpler explanation.
And about Alexei Merzin, he's the kind of guy who would sit in the audience and then look at your screen and say, that's not the protein that you say you're showing. I'm looking at a picture of the protein. So that's.
And he'd be right.
He'd be right, you'd be wrong. Every time.
All right, so I guess a concrete answer to your question, why did they use cath instead of SCOP? It's because same author and because coverage. And not in that sense, but rather more proteins in the database sense. Okay, moving on to question 4 then. If we were to repeat this benchmarking effort, but now using a set of transmembrane proteins instead of what is predominantly cytosolic ones, would we expect the same performance? Yes, no, and why? Go for it.
Well, I don't think so because transmembrane proteins, I think very few of them are the structure itself, so then I guess there would be very few candidates.
Okay, so the answer given is that because transmembrane proteins are harder to crystallize and to determine the structure of, there are fewer structures for transmembrane proteins to put in databases to begin with. Very true. But let us assume for a second that we have a database of transmembrane protein structures, and we train or we benchmark against that database instead of the one given. What would be different and why? Go for it.
Transmembrane proteins have a lot of intermembrane domains that are roughly similar, 7 or 8 domains that go through the membrane. And they would all be homologous to each other to some degree, so you would expect that you would need to change your threshold.
All right, I'm going to pull this back to the definition of homology that we begin with.
Okay, similar.
Better, right. So homology, by definition, means that you share evolutionary ancestry. But there is far fewer ways of forming a stable transmembrane helix than there are of forming a roughly globular cytosolic protein. So the amount of structures that a protein can assume in a membrane is far smaller than the amount of structures that a protein can assume in free-floating cytosolic medium, cytoplasm. This means that for transmembrane proteins specifically, you observe a lot of convergent evolution. Right? Homology we use to detect divergent evolution, or rather to reconstruct this divergence, that we see that two things used to come from one ancestor and now are two separate units. Whereas with convergent evolution, you have the exact opposite. So things come together from different evolutionary lines to assume roughly the same shape or function. For transmembrane proteins, this happens more often than in cytosolic proteins. So therefore, we would expect to have more true homologs based on comparing a structure, even though they are not actually homologs. So here our ground truth is wrong more often. What we assume to be true, that the structures are similar, therefore they must be homologs, is not a true assumption anymore. What does this do to our confusion table? How do the cells shift? If based on sequence you would no longer predict homology, whereas your truth, which we now consider to be wrong, tells you that they are homologs. Yes?
There are a lot of false positives.
Other way around.
Oh.
Yes. It took Anton and me some time to figure this out over the break as well, but what we settled on is that because you now think things are homologs even though they aren't, based on their structure, which is our ground truth, and then our sequence analysis correctly predicts them to not be homologs, what you actually end up with is false negatives, which is counterintuitive. But that counterintuition is exactly because it's the ground truth that's wrong and not your predictions. So I'm gonna pick this up again. Here. And discuss some of these final points that I hope you also thought about while reading the paper. The label on this axis is the percentage of exceptions in error versus the percentage of curated exceptions covered. Has everyone read the section on these SAS corrections? I'll take that as a yes. So, the point that the authors make in the paper is that there are known exceptions to structures that are different, even though we know them to be remote homologs. And for some of these cases, CAT entries have been corrected to reflect this new knowledge based on information outside of structure. And in some of these cases, they have not. And for the cases that have not been corrected in CAT itself, there is a set of methods with an increasing stringency that allows you to account for things not having a similar structure and still being homologous. And this is what these SAS rules are for. Coming back to the transmembrane discussion that we just had, if your ground truth is wrong, then your interpretation of your predictions will also be at least as wrong. So by correcting the ground truth model they derive from past using these SAS models, what they do is allow their interpretations to be more accurate. In the interest of time, I don't want to spend too much more time on this, so we will continue to this bit. We've already seen this graph before. This is on NR35. And now have a look at this one. What's going on here? Why is this such a mess? To refresh your memories, what would a perfect line look like here? So for perfect method, you will have no errors per query and you will have maximal coverage. Right? So you go straight up, and then only once you start changing negatives to positive predictions, you start going right. These methods clearly aren't perfect, but they're rather jiggery as well. And this is because these are really, really difficult predictions to make. For NR10, looking for the most remote set of homologs that you can think of with these methods, it is really difficult to get reliable performance when you make tiny little changes to your threshold. I don't know how much more time we should spend on this, so let's just move on. Main points, to refresh your memories before I send you off for lunch. Programming class, lunch comes after. Question?
Project work.
This one.
Programming comes after.
These points reflect different thresholds for the methods. So when you slide your threshold up, you will change the predictions for one or several proteins from negative to positive. And then what you see here is that with the best method here, TRC and Compass, the FoB PoB best methods, you make relatively few errors per query for relatively many coverage. I mean, it's still not good numbers, right? If you have a coverage of 0.2 and an EQ of 0.1, first of all, that means that 1 out of every 10 hits is actually wrong. And it means that also 1 in 5 of your actual homologs you still manage to detect. Does that answer your question?
Yes.
Good. Right, then to refresh your memories on the main points. Benchmarking is very, very common and also very, very important for any work you do in the field of bioinformatics. This needle in a haystack problem of finding the few actual homologs in this giant sea of possible hits is made much more difficult by having to balance sensitivity and specificity at the same time. Right? You can maximize one at the cost of the other, but the difficulty here lies in maximizing both. How you interpret your score and how you are able to score at all depends on your gold standard. So what you assume to be true, this is necessary for a benchmark, even though you usually know that your truth isn't as true as we would like it to be. We've discussed very many different ways to statistically interpret your confusion tables. So there's all these measures of sensitivity, specificity, EPQ, etc. And we've shown you 3 different types of plot that you can use to visually inspect what is actually going on with your method. And we have discussed the read-it-all paper of remote homolog detection. And I would really hope that the thing you take home from this is that profile methods are the best way to go for definitely remote homologs, but presumably for closer ones as well. And I think that is it. So, thanks for your attention, and see you in the program soon.
Project work, not programming.
Well, some of them are programming.
Later.